Hello, thank you for attending my talk on enabling real-time irregular data flow pipelines on SIMD devices. My name is Tom Plano, and this is work that I did in support of my PhD under my advisor Jeremy Buehler at Washington University, with support from the National Science Foundation. Let us begin with a motivating example, namely gamma ray burst detection. The job of a gamma ray burst detection device, like the Fermilab photo on the top right, is to collect high volumes of energetic photon events and process this stream of events to decide if a gamma ray burst was observed. If such a burst was observed, the device must notify ground stations with a very short deadline of less than 1 second per photon. GPUs, which are commonly used to keep up with the data volume for such high volume tasks, can't guarantee this 1 second per photon deadline for this specific type of application. The application model that is used to do this filtering, processing, and notification for a gamma ray burst telescope is one whereby many computational nodes are connected in series with queues, where items are transformed or dropped based on certain parameters. Items flow from low-ordered nodes to high-ordered nodes and are transformed along the way. A generalized data-dependent streaming application can be fully defined using only the following set of definitions. 1. A node, which is the schedulable unit of computation, which will be strung together into a pipeline. 2. The vector width, V, which is the device vector width for each node in the pipeline. Hypothetically, it could be a variable vector width, but in practice, we find that it is often a set vector width based on the device in question. The gain of a particular node is the average number of outputs per input for that node. Nodes are allowed to filter and expand input arbitrarily based on the content of the data packet they are processing. The execution time of a node is the time it takes to process V or fewer items. The inter-arrival period is the time between item arrivals into a particular node, and more specifically, inter-arrival period 0 is the time between item arrivals into the pipeline as a whole. Finally, we have a deadline, which is the time after an item arrival when outputs must be produced if we are to meet the constraints of our system. The device model we concern ourselves with is a single core sequential model with preemptive capabilities and user accessible interrupts, along with hardware vector operations. The main focus of this work is commodity GPUs, which we acknowledge do have some limitations on the ability to do preemption and user accessible interrupts. Part of this work is to motivate that these facilities would be not only useful but practical and provide specific performance improvements if they were made available to developers. The driving research question for this work is, how do you safely and efficiently process items in a SIMD data flow pipeline that exhibits the following properties? 1. Pipeline nodes may filter or expand input during processing due to data irregularity. 2. Work items arrive at regular intervals. And 3. Work items are deadline constrained. Safety and efficiency must be more rigorously defined in order to answer our driving research question. A safe pipeline rarely misses item deadlines and has a miss fraction that can be tuned for a very low percentage of the total inputs that it receives. An efficient pipeline minimizes the fraction of the processor it utilizes. Intuitively, high vector occupancy leads to lower processor utilization, and low utilization means potentially more time for other processes on the system to utilize the device in question, or potentially more time that the device can be powered down into a low-powered state, such as in the case of the gamma ray burst detection system. I will now walk through some of the key observations and hypotheses that we made. The first observation is that an existing throughput-oriented scheduler does not respect item deadlines. Nodes in a throughput-oriented scheduler may wait an arbitrarily long time before firing, especially if they are deep in the pipeline and the pipeline has significant filtering behavior, because the throughput-oriented scheduler is designed to maximize device occupancy at all costs. We then observe that there is a term we call system slack, which is the difference between an item's deadline and the amount of time it will take to process that item, which is the sum of TIs. This system slack could be thought of as the amount of time an item can wait around in the pipeline before blowing its deadline. Our hypothesis is that we can augment a scheduler by allocating slack intelligently among various nodes in the pipeline as a waiting time WI, in an attempt to enable a deadline awareness for the scheduler. Specifically, we're going to enforce that a node must fire in a duty cycle of wait time I plus execution time I. This waiting time allows a deadline occupancy trade-off. The node has a specific firing interval of WI plus TI, at which time it will fire, regardless of the number of items in its queue. In this way, we can ensure that no particular item in any queue gets left to wait for too long, while also trying to ensure that when we tune the Ws, that the nodes that fire will be mostly full when they do fire. The primary contributions of this work are an optimization problem that, given the inputs for a particular pipeline configuration, that computes the value of the wait vector that numerically minimizes process utilization for that pipeline while meeting item deadlines with high probability. Informally, we define this optimization problem with an objective function that encodes device utilization, subject to all wait times being positive or 0, the average number of items delivered to a node being less than its vector width on average, so the node doesn't back up. The relationship between two adjacent nodes must be stable, and by ensuring that the worst case execution does not exceed stated deadlines. This stability relationship is tuned with a user selectable term BI for each node and allows us to adjust what the acceptable misfraction for a particular pipeline is. We then developed an event-driven simulator to model the interrupt-enabled GPU hardware. This simulator loads the integer-valued configuration of a pipeline and simulates arrivals based on the computed wait times from the solver. Node's output is controlled by a random process that respects their gains, and we're able to report statistics on the device utilization and miss rate at the pipeline level and the per node level. In order to decide if our system is actually an improvement over other solutions, we develop an optimization problem called the monolith, which treats the pipeline as a fused set of operations in a black box. Items can only wait at the head of the pipeline, and nodes process all available input before transferring control to the downstream node. When the last node terminates and all of its inputs have been output, the pipeline sleeps until enough input has accumulated at its head. We believe that this model of computation is in line with the style of computation that is typically associated with GPU, where you batch process in inputs without introspection to what is actually happening in the kernel while it's processing. We now move on to examine a few results. Specifically, we are going to present a nucleotide blast test case that was implemented on an NVIDIA GPU in order to accurately predict the number of cycles and the average gains that each node in the pipeline requires. Specifically, we then tuned the BI parameters so that the misfraction of the weight solution did not exceed roughly 1.5%. Here, we present the surfaces for both enforced weight solution and monolith solution over the tau naught deadline space. As you can see, there is a clear region for which the enforced weight solution outperforms the monolith solution as far as device utilization. Remember that lower device utilization is better as both of these configurations are meeting their deadlines. To further illustrate the region in which the enforced weight solution is superior to the monolith solution, we can look at the delta surface, which is the subtraction of the two device utilization surfaces from the previous graph. All areas in which the green delta surface is above the black zero surface are regions in which the enforced weight solution produces a lower device utilization for the same miss rate. In conclusion, we have formulated an optimization problem that models the real-time behavior of vector devices for pipelines that can meet deadlines. We've also formalized a competing model that can also meet deadlines as a point of comparison. We finally demonstrated the improvement region for the enforced weight solution in both numerical solutions and simulation. For future work, we leave the refining of the BI usages in order to give stronger guarantees about expected misfraction. Additionally, we leave the exploration of heuristic real-time schedulers for GPUs. These are of interest because they may enable testing on real hardware in the immediate future without explicit device support for user preemption and interrupts. Thank you for attending this talk.